All right, so I'm going to do some more example problems. Now, I keep saying the same old thing, right? Force diagrams. But sometimes you can do some analysis even before you get to the point of drawing a force diagram. And here's an example. A 10.2 kilogram block is held in place by massless rope passing over two massless frictionless pulleys. Find the tensions and the force. So what's so great about massless ropes and massless pulleys? Well, we know that, well, I'll get to it, but just remember what we learned in the past. Okay, so here, what has to be, according to Newton's third law, what has to be true about F in T5? So pause your video and vote, please. Okay, so that should be obvious, right? F equals T5. All right, now, thinking about massless ropes and massless pulleys, what has to be true about T5? In other words, what other tension is equal to T5? So you should just be so pause your video and vote or figure it out. Okay, so what we've learned in the past is T5 has to equal T2, right? Because it's the same piece of rope over a massless frictionless pulley. So look at what we've done already. We figured out that F equals T5, which equals T2. So we're doing great. Now let's just keep going. See how much we can do before we have to draw a force diagram. What does T2 equal? So just follow that rope again. What does T2 have to equal? It has to equal T3. Because this pulley is massless and friction, so same piece of rope, right? So T2 equals T3. So we figured out 4 forces already. Awesome, right? Oh, you didn't see that? All right. So can we do anything else? Can we do any more? Or do we have to draw a force diagram? Well, we know that these things are equal. We don't know the numerical value yet. And we don't know T1. So now we have to draw force diagrams. Okay, so how many force diagrams do we need? I mean, just think of what we don't know. We don't know T1, we don't know T4, and we don't know the value of anything of those, right? So how many force diagrams do we need? Well, 3. Right? We got to get T4, so that means that this is going to be the object. We don't know T1, that's going to be the object, and then we need a force diagram for that. So 2 pulleys and 1 object. Okay, so pause your video. And you draw the force diagrams for both pulleys and for the block. All right, we're back. So let's do it. All right, so what's the only force acting on the block? We have T1 going up, and we have gravity going down. So there we go. So for the block, we have T1 going up and the weight going down. Okay, look at this pulley. What are the only forces? We have T2 up, we have T3 up, we have T1 down. So T2 up, T3 up, T1 down. Look at the large pulley. We have T4 up, T2 down, T3 down, T5 down. Wow. And remember, they said they're massless pulleys, so that's why we don't have the weight of the pulley. Okay, so this is in equilibrium, right? This is not accelerating. So what's T1? T1 is just the weight, right? So it's 10. So T1 is just the weight, which is the mass times g. So 10.2 kilograms times 9.8 meters per second squared. I think it's 100, right? That's 100. 100 newtons. Okay, so now we know, so T1 is 100 newtons. Okay, now let's go here. T2 is equal to T3, and that has to equal T1, right? So for this one, we have T1 equals T2 plus T3. These are equal, right? And this is T1 is 100, so these guys have to be 50, right? So T2 equals T3 equals 50 newtons. And then over here, T4 has to equal 2, 3, and 5. So T4 is equal to T2, 3, and 5. Okay, 2 is 50, 3 is 55. Where'd 5 go? What? What? Hold on a second. T4, where the heck is T5? I can't believe it. Oh, right there, sorry. Okay, so T5 is, all right, so all of these are 50, right? So T4, right? 50, 50, 50. Sorry, I couldn't even read it up there. 150 newtons. Yay, okay, so there you go. So what's the moral of the story? Sometimes you can do a lot of analysis before you even do the force diagrams. But I mean, you know, eventually you're going to need to do the force diagram. Okay, oh yeah, so I'm going to do some homework problems now. These are challenging homework problems. So read it while I erase, please. Two packages start sliding down a ramp. Package A has a mass of whatever and coefficient of friction 0.2. Package B has a mass of whatever, coefficient 0.15. How long does it take package A to reach the bottom? Now here's the important thing. Package A's coefficient of friction is larger than package B's coefficient of friction. So what's going to happen? So package B is going to be smashing up against or pressing against block A, right? All right, block B wants to go fast, but block A is in the way, you know? So B is pushing against A the whole way down. Oh my gosh, okay? So, but now it says how long does it take package A to reach the bottom? So it sounds like a kinematics problem, right? So, you know, so kinematics all the way, right? And so we're just going to, okay, so let's do it. So which kinematic equation are we going to use? You know, we know the distance, right? We know the distance. And the initial speed is 0, right? It says two packages start sliding down. So we know the distance. We know the initial velocity is 0. Long one, right? Long one. Okay, and we're going to do it like we always, I mean, we usually do these. Just think of this as one dimension, right? We don't want to do a two-dimensional problem if we don't have to. So we're just doing this, right? We're tilting the axis. This is the x-axis. This is the y-axis, okay? All right, so here's the equation. So x final equals x initial plus v initial delta t plus 1/2 a delta t squared. Okay, now I'm going to be super horrible. I'm not even going to draw a pictorial representation. So this is the initial point, this is the final point, all right? So the initial point, x0 equals v0 equals t0 equals 0. That's nice, right? So goodbye, goodbye. And we're trying to, right, and delta t is just t1. T1, okay? So we're trying to solve for t1, so multiply by 2, divide by a. So t1 equals 2x1 over a square root. All right. I hope you can, you should be able to do this by now pretty much in your head, you know, the kinematics. Okay, so we got to find A. Now, what's true about A, the acceleration for this block and this block? I mean, do I have an A for this, which is different than the A for that? No, because remember, this is pushing up against this one. So each block has the same acceleration, okay? Well, that's nice, right? That's nice. Well, here we go, folks. So what are we going to do now? We've got to draw the force diagrams. All right? Now, you know, well, we're going to have to draw two force diagrams. And you'll see, all right? You'll see. So here we go. But let's draw, I mean, you know, how long does it take block package A to reach? You might think we only have to draw the one for A, but when you do that, you realize you need the other one as well. So let's just do it. Okay. Oh, boy. So, pretty awful. Who cares? Okay, so let's do, this is, drives me crazy. Okay, B, let's do B. Okay, so tilted coordinate system, right? So this is B. So what are the forces acting on B? Well, there's friction, there's weight, there's normal. What else? One more. Well, if B is pushing on A is pushing on B, right? So, okay. Okay, so for B, we have the normal. We have the normal, might as well, yeah. We have the weight, right? So this is the MBG. We know we're going to have to resolve it. Okay. We have two, so I'm going to draw like that. So we have FKB. And we have FA on B. All right. That's it, right? Okay. So you know what to do. We have friction, so we're going to do the Y first. So the sum of the Y forces. Okay, is it accelerating in this direction? No. Okay, so we have the normal up. And we have this, which is MBG cos theta. That equals 0. So the normal equals MBG cos theta. And we've already seen that, right? That's nothing new. All right, now the X, which is going to be the mass. So the sum of the X forces equals MBA, right? Because it is accelerating, you know. Okay. Well, we have, what is this? It's the weight times sine theta. So MBG sine theta. MBG sine theta. Then we have both of those things, right? So we have minus F A on B and minus FKB. Okay, now let's just, what's FKB? FKB is mu K NB, which is mu K MBG cos theta. So let's erase this and put minus mu K MBG cos theta. All right. Wow. All right. So, you know, we're trying to get A. We don't know what this is. And we, all right, you kind of expected that, right? All right, so that means we have to draw another force diagram, which you should have expected. Let me just check, make sure I didn't mess up. Yeah, I did great. All right. So let's do the force diagram for A. Okay, so as always, we have normal A. So here's MAG. So we have components. Now, again, we have FKA, but we also have, remember, B now is pushing down on A, right? A was pushing up on B, B is pushing down on A. Newton's third law. So we have FB on A. What did I do that for? I don't know. Did you hear? FKA, FB on A. Yeah, right. Okay, so kinetic friction, normal, weight, B is pushing down on A. All right, so here we go. Let's get the friction, just get it over with. So the sum of the y's equals 0, right? It's not accelerating in this direction. What do you say we just be fast? So you know that this has to equal this, which is MAG cos theta. So therefore, the normal, crazy, normal A equals MAG cos theta. No surprise there. All right, now we can do the x's. Again, which equals MA. All right, so we have FB on A. FB on A. Going down, we have MAG sine theta. And we have minus the friction, minus FKA. All right. Now, come on, we can just do this, right? What's minus FKA? Mu k times the normal. There's the normal. So let's just do it. Minus mu ka times the normal. MAG cos theta. All right. Okay, so there we go, right? Now, what a mess. We're not even done yet. So we're supposed to solve for A, you know? I mean, all right. So A is an unknown, and this, right? We don't know what this is. So we have two equations, two unknowns. So how are we going to solve that? Well, I'll show you how I did it. You don't have to do it my way, but before I do anything, we've got to get some room. So we've got to do some erasing. Don't erase anything important. And we're going to use Newton's third law, of course, when we solve the equations. All right, here we go. Okay, so this one. So this one says MBA. MBA, I'm just going to copy it, equals MBG sine theta minus FA on B minus mu K. Okay, so all I did is copy it. Now I'm going to copy this one. MAA equals, I'm going to switch the direction. I mean, I'm going to put this first, though. You'll see why. equals MAG sine theta plus FB on A minus mu KA MAG cos theta. Okay, now, what am I going to do? Well, again, we're trying to get A, right? Now, how does A on B compare to B on A? Equal and opposite, right? Equal and opposite. Okay, sorry, these are magnitudes. Yeah. Okay, so I took care of the directions already, right? When I did my force diagrams, I took care of the directions. So how does this magnitude compare to this magnitude? Well, they're equal. Agree? They're equal. So what if I just add both equations? What's going to happen to this and this? They're going to drop out, right? Because the magnitudes are equal. One has a minus, one has a plus. So they're going to drop out. That's great, right? That's great. So let's do it. So this is going to be, let's kind of do something in our head too. This is going to be MBA plus MAA. The same thing as just A, MB plus MA. Okay. This is going to be MBG sine plus MAG sine. That's going to be just the same thing as G sine theta, MB plus MA, right? Okay, that's going to kill, goodbye. And this is going to be, you can figure it out. So it's going to be minus minus G cos theta, mu KB MB plus mu KA MA. Okay, so, wow. So all I'm saying is, if we didn't know that this magnitude was equal to that magnitude, we'd have 3 unknowns. And we couldn't solve it because you need at least 3 equations to solve 3 unknowns. So you had to use Newton's third law. Okay, now, we want to get A. So we're going to divide by MB plus MA. So divide the whole thing by MB plus MA. All right, so you do that, and you don't get 1, like that other problem we did. So you plug in everything, and you get 1.817 meters per second squared. So then you just plug it in. So we had T1 equals 2x1 over A. So you just plug everything in, and you get the answer. Now, there's a lot of math to this one, right? And so, you're going to have problems like this. And so what I would recommend you do, all right, you know what the answer is. You kind of know how I did it. You might not have followed every little thing I did, but that's okay. You need to do this on your own. And you need to go through all the math and make sure you can do it by yourself. That's the important thing. So please just do it yourself, all right? Make sure you can do it. That's what's important about taking this class. You learn how to solve these really, really long problems. Okay, let's quit. I think that was about a half an hour.